This is Unit 9, Example 1. So this is on page 170 of our packet, and it's about living with parents. So we read that a surprising number of young adults, ages 19 to 25, still live in a parent's home. A random sample by the National Institutes of Health included 2,253 men and 2,629 women in this age group. The survey found that 986 of the men and 923 of the women lived with their parents. Is this good evidence that different proportions of men and women live with their parents? How large is the difference between the proportions of young men and young women who live with their parents? So this data is categorical data. They're asking men and women, do they live with their parents? So we look at proportions. And so in step 1, we want to define our two proportions. So proportion 1 is the proportion of men ages 19 to 25 living with their parents, and proportion 2 is the proportion of women ages 19 to 25 living with parents. There's no particular reason I chose group 1 to be men and group 2 to be women, just in the order that it was in the word problem. You could do it in either order. So they ask about if there's good evidence that different proportions of men and women live with their parents. So of course our null hypothesis is always that the proportions are equal. So we always assume equality in the null hypothesis. So for age 0 for the null hypothesis, no change, we say proportion 1 equals proportion 2. Since they ask if different proportions and not more or less than, our alternative hypothesis is that proportion 1 is not equal to proportion 2. So step 2, we need to collect the sample proportions. So remember when we do a sample proportion, we put a hat on the P. So P1 hat is the sample proportion from the men, and P2 hat is the sample proportion from the women in the survey. So the men living at home was 986 out of 2,253. So if we convert that to a decimal, that is 0.4376. And the proportion of women living at home is 923 out of 2,629. If we divide and convert that to a decimal, it is 0.3511. So we see it looks like a higher proportion of men live with their parents. So then we want to think about, well, what's the difference in our sample proportions? So we subtract P1 hat minus P2 hat, and we get 0.4376 minus 0.3511, or 0.0865. So what this tells us in our sample data, the difference in our samples between men and women living at home is 0.0865 as a percent. This would be 8%. This is our sample data, so it's not the whole population. So we have to remember we're going to use this sample data to try to make a prediction about the entire population to say, is this a significant difference or not? So you can use your graphing calculator or StatCrunch to find the z-score. So on the TI graphing calculator, you could enter stat button, arrow over to tests, arrow down to test 6, the 2 proportion z-test, and put in for group 1 the male data. So x1 is the numerator and n1 is the denominator. For the female data, x2 is the numerator and n2 is the denominator. Choose the proportions are not equal and then calculate. And you'll see you get a z-score of 6.1782, pretty far from the center, and an extremely small probability. Let's look at how we would do this in StatCrunch. So StatCrunch will give us the same results. So you open a new window in StatCrunch, and you can go into Stat, and Proportion. So we go to Z-Stats, Proportion Stats down here, and we're working with 2 samples, so we choose 2 samples, and we say with summary. With data would be if we were typing in a long list of data, if we had all the survey data to enter. So we choose with summary, and then sample 1 is what we decided was the men, so this is like our x1, n1 on the calculator. So the number of successes is counting the number of men who answered yes to the survey, that they lived with their parents, and the number of observations, that's like our n1. And then sample 2 was the women living at home, so our successes, meaning the women who answered yes, was 923 out of 2,629. And then we're doing a hypothesis test, so we check the first bubble, And then they say P1 minus P2 equals 0. That means no difference. And then our alternative is that P1 minus P2 is not equal to 0. So StatCrunch writes this in the alternate way. If you look back at your vocabulary, page 169, you see that there's two different ways we could think about this. Saying that the difference in proportions is 0 is the same thing as saying the proportions would be equal. And then I'm going to add a p-value plot as my optional graph. So if we go to compute, StatCrunch will give us the p-value and all the data, and you might need to stretch to make your box bigger. And it's telling us a very small p-value, the same result we saw on the graphing calculator. It's telling us the z-stat is 6.1782, again the same result from the graphing calculator. And so we know this is unusual or significantly different. And if we arrow to the right, we can see here's the graph. And remember, this is a not equal to alternative hypothesis, so it's two-sided. So it could be that we're on the left side where there's a negative difference, meaning P2, the women group, had a smaller proportion, or it could also open the possibility that the men had a larger proportion, which is the case we saw in our sample data. So we see our shaded areas are so small they look like little dots out here, and so we see this is unusual to be 6 standard deviations out. So this small p-value is used to make our conclusion here. And so step 4 is to state a conclusion using the p-value to make a decision. So we say the very small p-value indicates that it is unlikely that the sample data came from the population described by the null hypothesis. So it's unlikely that there are equal proportions of men and women living with their parents. This is strong evidence against the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis. So remember, we're never going to say for sure that the null hypothesis is true, and we can't say for sure that the alternative hypothesis is true, but we can say there's evidence against the null hypothesis in favor of the alternative hypothesis. So remember, a small p-value leads us to make conclusions in favor of the alternative hypothesis, and we are comparing here to alpha equals 0.05 by default. So we assume 95% confidence if there's no other value given. Okay. Example 2, we're going to calculate confidence intervals for two proportions. So question A tells us from a sample survey the data about rap music among young city residents and young rural residents. And so if we let P1 be the proportion of young city residents who listen to rap, that is 368 out of 634, or 0.5804. And the proportion of young rural residents who listen to rap is P2 hat, 130 out of 567, equals 0.2293. And this is just the data from the word problem. So we can do this in our TI calculator. You could also do the confidence interval by hand using the difference and the formulas in the vocabulary section. And so using our TI calculator, here we go. We would put in the data in the same way, except we go to stat, tests, and then you'd scroll down to choice B, the 2 prop z interval. And again, we think about it in terms of x1, n1 being the first group and x2, n2 being the second group, and then you choose confidence level 0.90. And what this gives us is a range of values from 0.30778, so around 30%, to 0.39455, so around 39%, where we're confident the difference in the population proportions lie. So in this case, we're 90% confident. And so let's go look in StatCrunch. If we do the same calculation, we'll get the same results. So we can exit out of our previous graph. And then we go to stat and we choose, again, proportion stats to sample. And then we're going to put in, just in the same way, our successes and observations. So here, our successes for group 1 was the number of young city residents who said yes, they listened to rap. So that was 368 out of 634. And sample 2 was the rural residents who listened to rap. So 130 said yes, they listened to rap. And then 567 were the total there. And then instead of a hypothesis test, we're doing a confidence interval. And we're trying to predict what's the true difference in these two populations, these two groups. So change our confidence level to 0.90. And you can also check under optional graphs the confidence interval plot. And if we go to compute and stretch out our graph here, we see we get the same lower limit and upper limit as the TI calculator results. So again, around 30% is the lower limit and 39% is the upper limit for the true difference. So somewhere between 30 and 39% more urban young people or city young people listen to rap than rural young people. If we want to see what this looks like on a graph, if we scroll to the right, it's showing us that the plot would go from 0.30 down here up to around 0.39 over here. Okay, let's go back to part B, which is another confidence interval question. So here we're looking at this government survey, and so they surveyed 6,889 female high school students and 7,028 male high school students. And they're asking if they met the recommended level of physical activity. And note, these are very high levels, at least 60 minutes of activity. They make you breathe hard on 5 of the past 7 days. And here we're asked to give a 99% confidence interval. So this is going to be a higher confidence level and a wider range of values. So if we calculate the proportion of male high school students who meet the recommended levels, our sample P1 hat is going to be 3,078 out of 7,028, and that reduces to be 0.43796 as a decimal. And then the proportion of female students is 1,915 out of 6,889, or 0.27798. And so on the TI calculator, we go through the same process of the 2-prop z interval, and then we put in our data in the same way, and we change the confidence level to be 0.99. And so that gives us a range from 0.139, so around 14%, to 0.18062. So somewhere between 14% and 18% is the difference between the proportion of male high school students who meet the recommended levels and the proportion of female students who meet the recommended levels. And so this is a pretty wide interval, and so that's why we're able to say this with 99% confidence. If we were at 90% confidence or even lower, our interval wouldn't be as wide, so it would be smaller percentage differences. So we go into StatCrunch. We can exit out of our previous graph. And we run this in the same way. We go to Stat, Proportion Stats, choose samples with the summary data. And our successes here for the male, group 1 is 3,078 out of 7,028 male students. And sample 2 for the female students is 1,915 out of 6,889. And then we're doing a confidence interval, so we choose the confidence interval, the second bubble, and we change our level to be 0.99% confidence. And we can go to compute, and we see here's our upper limit and lower limit, so we get the exact same values as with the TI calculator. So again, you can use StatCrunch or the TI calculator to do your calculations here. Example 3 is looking at credit card use at a department store. So example 3 asks this question, are shoppers more likely to use credit cards for impulse purchases? And we're given this data of it's a two-way table of the credit cards, and then did they use a credit card, yes or no? And then the other question was an impulse purchase or a planned purchase. So here we want to compare impulse purchases and planned purchase. So notice I did the totals on the side. So the total impulse purchases is 13 plus 18 is 31. And the total planned purchases 35 plus 31 is 66. We also want to remember that we're at 95% confidence by default. So alpha is going to be 0.05 that we're comparing to. So step one is we have to state our hypotheses. So they ask here, is the difference statistically significant? So our alternative hypothesis is not equal to. We're saying, is group 1 different from or not equal to group 2 in the proportion of purchases that use credit cards? Here I call group 1 the proportion of impulse purchases because it was the first row in the table. Group 2 is the proportion of planned purchases because that was the second row in the table. You could reverse these and it would make no difference in your. If we look here at the sample proportions, we're using the data from the survey. So P1 hat is 13 out of 31, and that's 0.4194. P2 hat is 35 out of 66, so 0.5303. And then we find their differences. Notice that the proportion of impulse purchases using credit cards is lower. So the difference when we subtract the sample proportions is negative. So this would indicate that impulse purchases are less often using credit cards from their sample data. So now to assess the evidence, we need to do a hypothesis test. So on the TI calculator, you'll go stat, tests, and again choose test 6 for the 2 proportion z-test. Our first group is 13 out of 31, so we say x1, the numerator is 13, who used a credit card out of 31 total in the impulse purchases group. Group 2 is the planned purchases, so our numerator of the proportion is 35 out of 66 denominator, and we set our proportions not equal. And so we get a z-score of -1. It's negative because there was a higher number of planned purchases using the credit card. So when we did group 1 minus group 2, we ended up with a negative because group 2 had the higher proportion. And our p-value is 0.3081, so above 0.05. Let's go look at how we do this in StatCrunch. So again, we go to stat, proportion stats, to sample with summary. And our successes are the group 1, the impulse purchases, so the same 13 out of 31. And for group 2, it is 35 out of 66. And then we're doing a hypothesis test. So again, we're going to set the null hypothesis to have the difference is 0. That's the same thing as saying P1 equals P2, because if they're equal and we subtract, we get 0. And then we keep our alternative hypothesis not equal to. If we had more than or less than, we would click here and change to be a different inequality. And then we can compute. And so we see here we get the same results as from the calculator. Our z statistic telling us how many standard deviations is a little bit more than -1 standard deviations, and our p-value is 0.3081. So the p-value, remember, is telling us the likelihood of getting results like the null hypothesis. So it's a high probability that if the null hypothesis was true, if there was no difference, that you would get results like this. One reason could be because our sample size wasn't very big. If we had larger than 31 and 66 in our sample sizes, we might find significant differences. But in this case, the samples aren't large enough to find it unlikely that the null hypothesis is true. So this is reasonable that the null hypothesis could occur. It's not in our 5% unusual range. So we're going to use the p-value to state our conclusion. So we would need a p-value less than 0.05 to reject the null hypothesis because we need to be 95% confident. We do not have enough evidence against the null hypothesis, so this means we cannot reject in favor of the alternative hypothesis. In other words, we keep the null hypothesis. Notice we're not saying the null hypothesis is true, it's just there's enough likelihood that it could be true. So in the group work problems and the lab assignment, you have some similar questions to work through. You can use Graphing Calculator or StatCrunch, and make sure to check if you're doing a hypothesis test or a confidence interval, because that determines which test you run.